All right, so that's about as big as it's going to be. I can zoom in some on the wall, but I won't be able to zoom in a lot on this part. At least I don't think I can. Maybe I can zoom in some. Make it a little bit better. How's that? That's not too bad. Again, if you have problems seeing it up here, feel free to open it up on your laptop in front of you. Today we are covering section 1.2, which is all on functions and graphs. So we will have some definitions to start off with, and then we're actually going to work some of this out. Functions they can be confusing, but I think once you let me explain it, I think it'll make a lot more sense. So a function is a correspondence between a first set and a second set, such that each element in the first set corresponds to exactly one element in the second set. What that means is in algebra, a function, it happens when you put in one value for x and you always get out the same value for y. Now, that doesn't mean you get out the same value in terms of what x is. But if I plug in 2 into an equation, I'm always going to get out the same answer. I'm not going to plug in 2 and get out 1 sometimes, and plug in 2 and get out 3 sometimes. Every time I plug in 2 into my function, I'm going to get out the same answer every single time. That's what it means to be a function. If you can plug in 2, and sometimes you get out 1, and sometimes you get out 3, then you are not a function. There isn't that correspondence between what you put in and what you got out. That thing that we put in, we usually call the inputs, or the x's, or the domain. Those all mean the exact same thing. Your domain is your inputs. Those are traditionally your x values if you're talking about an equation that has x's and y's, which I would say 85% of all the stuff in algebra is x's and y's. Your range then, which is the blob that's on the right-hand side, is what you're getting out. That's your outputs, your y's. Those are your range. Domains are your inputs. Range is your outputs. If you're ever confused on which one is which, the nice thing is that in almost every terminology you look at, they're alphabetical. X comes before Y in the alphabet. D comes before R for domain and range. I comes before O, inputs and outputs. So that's something that's really, really nice. So the blobs, what it's showing you is that every little circle in the left-hand blob corresponds to just one square in the right-hand blob. I'm not going to put this little circle in and get more than one square out. This little circle always takes me to this square over here. That's what it means to be a function. So if you're a visual person, then you can kind of see how that plays out visually. There's a little star definition over there talking about a relation. A relation is a correspondence such that each element in the domain has at least one element in the range. So a function is a special kind of relation. Because a function says that every domain corresponds to exactly one element in the range. A relation says at least. So there is a difference. All functions are relations, but not all relations are functions. Okay? All M&Ms are candy, but not all candy are M&Ms. See how that works? So a function is a more specific type or subset of relation. So sometimes during your homework and your assignments, you're going to be given a list of elements, or you're going to be given an equation, and you have to determine whether or not that is a function. And we're going to do that right here. Determine if the correspondence is a function or not. And they have a little diagram showing the numbers 1, 2, and 3 going to numbers 4, 5, and 6 for A. Shows that 1 goes to 6, 2 goes to 5, and 3 goes to 4 with those arrows. So based solely on that picture and the definition of what it means to be a function, is this correspondence a function?
Yes.
How come? Yeah. If I look at these numbers over here, they only go to one number on the right-hand side. So my domain only goes to one item in the range. I don't have 1 going to 6 and 1 going to 5. So yes, this is a function. Now for B, we have letters. It's still the same process. We have A, B, and C going to the letters E and F. So is this a function? No, because A goes to E and A goes to F. What that means is if you think about your function or your equation or whatever you want to call it being a machine, if I put A into my machine, I should always get out E. But sometimes I get out E and sometimes I get out F. And if that's the case, then that means I do not have a function. So we had yes on A, we have no on B. We got C and D as well. C, we have 10, 20, 30 going to X, Y, and Z. Oh, you can see the answer. What do you think C is? Is it a function or is it not a function? It is a function. Now you might look at that and say, well, wait a second. Nothing goes to Z and 10 and 20 both go to X. That's okay. The thing that you can't have happen is like on B. We had A go to 2 different things. That was the problem. A can't go to 2 different things, but 2 different inputs could give us the same output, and that is okay for a function. So this one, yes, is a function. Now this D1 is a little bit different and unique in that it's not showing you with a diagram or with a set of numbers. It's telling you what the domain is, it's telling you what the correspondence is, which would be your arrows, and then it's telling you what the range is. So your domain, or if you're thinking about the blobs, this first blob is the set of prices. The correspondence is the items purchasable at that price. And the range, so this over here, is the set of items. So basically we're thinking about 2 different groupings. We have prices and we have things that are for sale. Okay, so you're at the grocery store. Everything has a price. That's your domain. The range is the set of items that are for sale. And if the correspondence is the items that are purchasable at that price, do you think that that means that every price only goes to one item? I have $5 on the price tag here for this shirt. Is that the only correspondence that you think we could make? Another way of thinking of it is if you go to the store today, go to Walmart, and you see something for $1.99, is there only one item for $1.99? Is this candy bar, this Snickers, $1.99? Is that the only item in the whole store that's $1.99? No, because there's probably a Mounds bar or a Hershey's bar or a soda or something that's also $1.99. So each price, which is our domain, does not correspond to only one item in the range. And so no, it's not going to be a function. That'd be kind of weird to go into a store where everything had its own completely unique price and nothing was the same. So these are a little bit, I don't know, I guess unique, because in algebra we don't usually see just a bunch of arrows drawing and pointing to each other, think about things like that. Usually we're going to think about functions in terms of equations, or in terms of graphs, or in terms of sets of numbers. So hopefully from Math 20 or Math 30 or one of the other math classes you've had in high school, you've seen sets. These E and F are sets of ordered pairs. Because like I said, an X is your input and Y is your output. So really we can think about this with ordered pairs. And a set is indicated with these curly brackets. So in E, we have the ordered pair 520, we have the ordered pair 624, and we have the ordered pair 728. And we need to figure out if those three ordered pairs give us a function. And the way that we do that is we look at the X values. We have 5, 6, and 7. Right there, you should be done. 5, 6, and 7, are any of those the same number? No, they're all unique. So that means each one of those is going to go to something unique. So that is a function. We don't have 5 going to 20, and then 5 going to 24. That is where our problem would lie. Because then we would say, well, 5 can go either to 20 or to 24, and that's the issue, and that makes it not a function. Since 5 goes to 20, and 6 goes to 24, and 7 goes to 28, then yes, this is a function. So let's look at F. F, we have ordered pair 2, 4, ordered pair 2, 6, and ordered pair 6, 2. Is this a function? Why not? Yeah. If we put the 2 in, we're going to get out 4 sometimes, or we could get out 6, and that's the problem. These problems on this last one also asked us to list the domain and the range, which I know it doesn't say that on there, but on your homework, it will give you a set, and it will say, list the domain and the range. So let me zoom in a little bit. The domain is going to be your inputs. So for E, the things that you put in are your X's. So the list or the grouping of X's are 5, 6, and 7. That is the domain of your function. Those are your input values. The values that you get out are 20, 24, and 28. You do not have to list those in any particular order. Usually we do list them in descending order, or excuse me, in increasing order, where you have the smallest value on the left and you go up to your highest value on the right. But if I would have put that my domain is 7, 6, and 5, it would still be correct. Or that my range is 28, 20, and 24, it's still correct. Just in general, it's a good habit to write from smallest on the left to largest value on the right in that increasing order. For F, the domain is just 2 and 6. Yes, 2 is listed twice in our input values, but we don't have to list it more than once when we list out our domain values. We just have to list it that one time. So sometimes you will have to identify whether or not it is a function, but then you might have to give a little bit more information as well, where you do list out what the domain values are, or you do list out what those range values are. But hopefully that's not too horribly difficult when you're looking at an ordered pair. Are there questions on any of those before we move on? Yes?
When listed as
You definitely don't want to put parentheses because then you have ordered pairs if you're listing them like that. They should, I believe, give you the curly brackets and you're just filling in the middle. If they don't and it asks it for a set, then yes, you will do the curly brackets. But I can check at the end of class. I'm almost positive they give you those curly brackets. Good question. All right. So let's look at it with a little bit more algebra, because this is college algebra, so we're going to do algebra. The first thing to note is this function notation. This is the way that we indicate a function. As you've grown up and done math, you've probably seen most of your equations and things like that you do algebraically as y equals, and I'm just going to write down like this, y equals mx plus b. That's a general equation where we are talking about it in terms of y. But when we are talking about a function, we are going to talk about f of x. So f of x, the function in terms of x. But notice nothing changes. Nothing changes at all. Instead of saying y equals in our equations, we're going to say f of x. That's really the only thing that's changing here. It kind of looks like a semantic type thing, but it's really a different way of examining the same equations. So note over here that when we talk about ordered pairs, instead of talking about x's and y's, we're going to talk about x values and then the output that we got when we plugged that value into our function, or f of x. Again, it means the same thing, though. If you see f of x, think about you're trying to find the y value. All right, f of 0 and negative 7. Whoa, you can't see that. There we go. So the example that we see up here on the screen says, compute the following for f of x equals 2x squared minus x plus 3. And then you can't see anything else because if I show you more, then it gives away the answers. So I'm showing you right here that they want you to compute the function in terms of 0. That's what this is saying. The function in terms of 0. So if you're looking right here, if this was originally f of x, and I'm looking at the function in terms of 0, then what is the value of x in this case? Yeah, it's 0. So when I go to compute this, I'm going to look at the equation they gave me, but everywhere that there is an x, I'm going to put a 0. These are what I call plug and chug problems. The value that they give you inside of that parenthesis is what you're plugging into the equation in place of that x. So you're doing a substitution and then you're solving. Well, 2 times 0 squared is 0, minus 0 is 0, plus 3 is 3. So when x is 0, I get out that f of x, or f of 0 at that point, is 3. So I actually get this ordered pair of 0, 3. Now, your homework assignments on the Pearson site will be very specific in what they want. Either they'll want it just as a value, or they'll tell you they want it as an ordered pair. Okay? If they want it as an ordered pair, then whatever you plugged in for your x is your x, and whatever you compute out is your y. This kind of goes back to what you just asked a little bit ago. We'll have to use the parentheses. If you are asked for an ordered pair, you will always have to type in the parentheses. If you do not type in the parentheses and you just write 0, 3, then you have not actually given an ordered pair. You've given a listing of numbers. So that may sound like technical, but it's just what it is. If I gave you this as a test and you gave me 0, 3, I would count you wrong because that's not an ordered pair the way you have it written. So make sure if it asks for an ordered pair, you do include the parentheses. Okay? Let's do negative 7. because this one is one that will trip a lot of you up. F of negative 7. So, same exact process. Anywhere in the original equation we have an x, we're going to write negative 7. You have to be careful because the value that you are plugging in is negative. That you do not just drop it here when it says minus x, because what you have is minus whatever that x value is, which is also negative. So you're going to have to remember your double negatives. You're going to have to remember what happens when you take a negative times a negative. A lot of times I include this little chart to the side in my notes. I do it in 20, 30, 125, this class, where a positive times a positive is positive, positive times negative is negative, a negative times a positive is negative, and a negative times a negative is positive. Because I like to go ahead and take care of those double signs when they pop up throughout the equation or the problem. So 2 times negative 7 squared would be negative 7 times negative 7, which is 49. Don't take 2 times negative 7 and then square it. That's your order of operations situation where you have to do the exponent first. Negative and negative becomes a positive. And you keep going. 2 times 49, 98. So you get 108. Again, if it asks you for an ordered pair, you could give it as an ordered pair. Questions on those? I'm going to write the equation again since I moved my paper, because we're not done with this equation. Okay, what if for C we said f of 5a? Now it's not just a number that we're saying x equals, we're saying x equals 5a. And that's okay. We're going to still plug that in. We're going to do it the exact same way. We're just not going to get a nice number at the end. We're going to get an algebraic expression at the end. You're still going to have 2 times 5a squared minus 5a plus 3. You're still putting the 5a in anywhere that there was an x. And then you're going to simplify it out as far as you can. 2 times, well, 5a squared is 5a times 5a. That's 25a squared. Minus 5a plus 3. You simplify it, sorry, that's a really wonky 5, until you can't combine it any further. There are no more like terms. I can't combine an a squared with an a with a whole number, so this would be the final expression that we get. When you get an expression like that, they will never ask you for an ordered pair because it's not really an ordered pair in the general terms that we think about it. One more. F of a minus 4. 2 times a minus 4 squared minus a minus 4 plus 3. Notice I put that a minus 4 inside those parentheses. Because if I don't, then what I'm likely to do is say minus a minus 4, and that is wrong. I put that a minus 4 in parentheses so that I remember that this negative applies to the a and to that negative 4. That's called distribution. And I'm going to split my a minus 4 squared in that first bit. Because a minus 4 squared means I'm going to have a minus 4 times a minus 4. Who remembers what we have to do when we have a binomial, this a minus 4, times another binomial? Foiling. That's exactly right. Foiling. That's first, outer, inner, and last. It's a specific way that we can multiply two binomials together. So, I'm going to leave that 2 out front for right now. First means you're taking the first terms and multiplying them together. Then you're taking your outside 2 terms and multiplying them together. Your inside 2 terms and multiplying them together. And then your last 2 terms, negative 4 and negative 4, will give you a positive 16. Now we're going to multiply everything inside the parenthesis. Well, I'm going to combine it first, I guess. 2 times a squared minus 8a plus 16 minus a plus 7. Then I would multiply everything inside the parenthesis by the 2 and combine like terms. So 2a squared minus 16a plus 32 minus a plus 7. Almost done, but I have a negative 16a minus a, which will give me a negative 17a, and then I have a positive 32 plus 7 will give me a positive 39. So yes, you have to do foiling. You might have to do distribution. That's what we did here, which is why I leave that negative outside so that I remember to distribute that negative inside. All of those tools that you've learned throughout your years of math will come back into play. Questions? All right. Let's graph something. Let's be done with the algebra for a minute. Let's do some graphing. Let's graph something. Here's the nice thing. Right now, if we were asked to graph anything, let me bring the paper down. The way you're going to do it is you're going to graph by using a table. We're going to pretend like you don't know how to graph anything. And maybe you don't. That's fine. Then this is a great starting point. Maybe you do know how to graph x squared minus 5. Maybe you know what that's going to look like already. That's great. But right now we're going to pretend like you guys have no idea what to do and how to graph this. So you're going to use what I call the table method, where you're going to have an x category. You're going to have your function category, which is where you write out your equation. And you're going to have your y, or you could say your f of x category, whichever one you're most comfortable with. And then here's what I always recommend doing. Anytime I make a table and I'm using points, or the point plotting system as I call it sometimes, I'm going to use 2 negative values, and you get to pick them. They're whatever you want. I'm going to pick 0, and then I'm going to pick 2 positive values. Generally, I pick negative 2, negative 1, 0, 1, and 2 because that keeps my x values small, which usually means my y values are also small, and I'm not graphing something out to the moon and getting these huge, outrageous numbers. Now, if we are plugging these x values into our function, then we are doing exactly what we were just doing on the previous problems. I'm going to find f of negative 2, which means anywhere that there's an x, I'm going to plug in a negative 2. And I'm going to solve and see what I get. Negative 2 squared is 4. 4 minus 5 gives me a negative 1 for my output, for my range, or my y value. And I'm going to do that again for each of these values. I'm going to find f of negative 1 by plugging in negative 1 into the equation and computing my output. And you just keep going until you have done all of your computations. So graphing by plotting points does take a little bit of time. But the nice thing about graphing by plotting points is you don't have to know anything about the graph or that equation or that function or anything else in order to graph it. We plug in values for the x and we see what's going on. I will go ahead and let you know that as we move through this class, though, you will get very good at identifying what these functions are going to do, what these graphs are going to look like. It is a huge chunk of college algebra. And we will learn lots of different methods and ways to graph. I know Kelsey asked on the first day if we need to get graph paper. And the choice is up to you. You don't have to get graph paper. It's not a mandatory requirement. If you don't have graph paper, you'll get pretty good at freehanding it. And you'll give yourself grace when it comes to freehanding your graphs. Just like I hope you'll give me grace because I will always freehand my graphs on the notes here. Once you have your table and you have your column of x values and you have your column of y values, what you really have is you have an ordered pair. When x is -2, y is -1. So I'm going to go graph that. When x is -2, y is -1, I plot that point. When x is -1, y is -4. 1, 2, 3, 4. When x is 0, y is -5. And I continue graphing. If I remember correctly, in this section, you don't actually do the physical graphing on the computer itself. You will fill out the table, and then you match what your table says to the graphs that they give you. You do get a parabola that opens upward that looks like this. Any questions on how we did that? Okay. So that's how you graph a function at this stage of the game. Here's the nice thing. Functions, like we saw at the beginning, functions take one x value to exactly one y value. That means we can actually test this using something called the vertical line test, which is where they give you a graph, and then you can determine whether or not that is a function. The vertical line says, or the vertical line test says that if you can draw a vertical line through your graph and it hits the graph in more than one spot, then it's not a function. It's not a function at all. So vertical line tests are super nice because on your XY plane, here's your X's and here's your Y's. If I have a big squiggle like that, and I draw a vertical line and it hits in only one spot, no matter where I draw that vertical line, then what that's telling me is that for this given X value, it's only going to hit my function in that one spot. And so it passes the vertical line test. So it is a function. Whereas if I have a squiggle that goes like this, and I draw a vertical line, then it hits the function or the graph there, and it hits the graph there, and there, and there. So for that one X value, I got 4 different Y values. So that is not a function at all. And that's why the vertical line test works. And it's wonderful because it makes spotting functions with lines, like when you're given a graph, super easy. So some of your homework and quiz problems, they give you a picture and they say, is it a function? And you draw a vertical line through it and say yes or no. Now, some of these graphs you might be, well, on this part I could draw a vertical line, like on B. If I drew my vertical line over here, well, it would only hit in one spot. But the vertical line test is if it can be drawn anywhere and it hits more than once, then it is not a function. So A is a function. No matter where I draw a vertical line, it's only going to hit my graph one time. B, though, is not a function. Even just looking at the y-axis there, it's going to hit 1, 2, 3 times in that one spot. So that is not a function. C is not a function. Again, just look at that y-axis. It hits twice. Circles are never functions because they always have an upper point and a lower point on the outside of that circle that's going to hit at any given x value. Now, E looks really wonky and weird because it's got all these sharp corner and it's got a flat spot and everything else, but that still is a function. It's not a polynomial, and that's what we'll learn about later on, but it is a function. Because if I draw a vertical line, I'm still only going to hit it in one spot. And then F is an even more unique situation, which again is not a polynomial, and we'll talk about that later on, but it is a function because here it's called a piecewise function, which means you have different pieces that meet together that make a function or that make a picture. Here we have an arrow or a part of a line segment or ray that shoots off to the left, and then we go all the way up really, really, really close to this point, but we're not actually at this point, which is why it has an open circle there. But it has a filled-in circle up here. And because it's filled in up here, if I draw a vertical line through there, I'm only actually going to hit that filled-in circle because I'm not including the open circle down here. So it would still only hit in that one spot. If, let me show you here, if I were to have a closed circle and I had a closed circle situation going on, then if I drew a vertical line, it would hit at both of those closed circles. Then it's not a function. But because this one was specifically open and that one was specifically closed, meaning it included the point at that y value, then it does pass the function test. We don't do a ton with piecewise, but we do interact with it a little bit, so I like to show it when we do. Questions on the vertical line test at all? All right. Here's some more notes. And again, feel free to write them down. Feel free not to. Feel free to reference my notes that are scanned in, whatever you'd like to do, because the rest of that page is all 100% notes. There's going to be times that you are asked to find the domain of the function or the range of a function. And here's the really nice thing about the domain of the functions is you're going to be given equations, like on our graph. Sorry, I'm going to cover that up for just a second. Like here, we were given the function f of x equals x squared minus 5. Okay? They told us that one. So the domain of that function is always going to be this negative infinity to positive infinity. That's interval notation. We covered that back in Math 20. If you didn't take Math 20, though, here, when you're coming straight out of high school, interval notation is something to definitely reference and get used to. I mentioned it a little bit right here. So that tells me that the smallest number is on the left. The smallest value for the domain is negative infinity, and the largest value is positive infinity, unless, and there are two cases where it's unless there is an x in the denominator. So you have some sort of a function where you're going to have something that looks like this. F of x equals 3 to the x. Notice how there's an x in the denominator. If there's an x in the denominator, then there's going to be some what I call trouble spots that you're going to have to get out of your domain. The other situation where it's going to affect your domain is if you have a function with an even-rooted radical, and there's an x underneath it like this. Even-rooted radical, so like a square root or a fourth root or a sixth root or something like that. Then you're going to have some trouble spots that you have to eliminate out from your domain. Otherwise, You can plug in any x value into any function and you're going to get out some kind of a y value. Always. These are the two special cases. X in the denominator or x under an even rooted radical. Whoops. So, I did put a star note there that you are using interval notation. And if we remember back interval notation, if we have less than or greater than, we're using the parentheses. Less than or equal to, greater than or equal to, we're using the closed-in squared brackets. Back in Math 20, when we talked about interval notations, we would combine different sets of numbers using two different, I guess, processes. I don't know how else to word them. We would talk about unions and intersections. And a union is where you take two sets, and I like to use the Venn diagram set up like this because I think it's helpful to understand the Venn diagram because it's a very visual representation, where you have set A and you have set B, and when you union them, you are combining them together. Think of like union, marriage. You're taking all of this person's stuff and all of this person's other stuff, and you combine them together, and that's a union. So if you're talking about unions in terms of sets or numbers, then we oftentimes will see it written over here in this set builder notation. And I know it went down to 2 lines, so I'm going to write it underneath so that you can see it all written out in one long expression. So set builder notation is where you have the curly bracket because that indicates a set. Then you have x such that. And then if you were doing a union, then x is an element of A or x is an element of B. This little wonky E means element of. So what that's saying is if you lie in the union, then you lie either in set A or in set B, or you could be in either, like you could be in both because there is that section in the middle. But you have to be in one of them in order to be in the union. So that's when you combine them. Intersections, though, are kind of just a special subset in the middle. Notice with the Venn diagram, we have set A and set B, and where they overlap here in the middle is actually the intersection. The intersection is symbolized with this upside down U. So we have A upside down U, or intersect B, is the set of X such that X is an element of A and X is an element of B. Those are the big difference. Or means union, or implies union, and implies intersection. You can think about it here in Joplin as street intersections even. If you're on 7th and Range Line, then you're standing in the middle of 7th Street and Range Line. You are part of both of those streets. You are part of 7th Street. You are part of Range Line. But if you move out of that intersection, then you're either on 7th Street or you're on Range Line, but you're not on both. The only way to be on both streets at the exact same time is to stand in the intersection. And so we can talk about intersections and unions with numbers as well. If you are asked to find the intersection or the union of two different sets, in your homework they'll give you the curly brackets and they'll give you the X such that, and then you fill in the rest as you encounter it. But when you see this curly bracket X such that, in the curly bracket, this is set builder notation. Up here, when we're talking about the domain and the range, you will almost always use the interval notation. And those are two different notations that, again, we do cover back in Math 20. All right. Let's finish these notes out and do a couple of examples of finding the domain. like we just discussed, there's only 2 exceptions for the domain not being negative infinity to positive infinity. So that's kind of your starting point whenever you're doing these domain problems. You're starting with everything, and then if there's an x in the denominator, like on these first 2, or if you have x under a even-rooted radical, then we're going to eliminate out some of these trouble points, okay? These bad spots, these trouble spots. So what ends up happening is if we look at this first example, we have f of x equals 1 over x minus 7. And one of the big rules in algebra is we never, ever, ever want our denominator to be 0. Like, that is a problem. And so if our denominator equals 0, then we don't have a function. It's not valid at that point. So we need to figure out, when does x minus 7 equal 0? Because wherever that happens, that is our trouble spot, and we need to remove that from this negative infinity to positive infinity. So if I have x minus 7 equals 0, then I'm going to add the 7 over, so I have x equals 7. So when x equals 7, then I get a denominator equal to 0, and that's the problem. So I need to eliminate this x equals 7 from my negative infinity to positive infinity. So how do I do that? Well, I'm going to have my domain, and I'm going to say, okay, well, what's the smallest value that x can be that works for this function? Well, the only value that doesn't work for this function is the x equals 7. So I'm going to go ahead and start at x is negative infinity, and I can go all the way up until x is 7. Now, we use this parenthesis here because I don't want to include 7 in our domain set. So if you use a parenthesis with interval notation, that means you do not include the boundary point, that end point. Then I'm going to union that and then do 7 to positive infinity. So we just talked about unions and how if you union 2 different sets or intervals together, then you are combining them. And if I combine these 2 different intervals right now, then I have everything from negative infinity to positive infinity except for this one single point here, which is 7. And that's what I wanted to get rid of. Because as long as I get rid of the point 7, everything else works for this function. And so this is the domain of that function. Okay? That was one of those exceptions to the rule. Now for G, if I look at it, you're like, oh goodness, there's a ton of stuff going on here. It is, but don't get overwhelmed. This problem only asks us to find the domain. So if we're finding the domain, it doesn't really matter what's on top. It just matters what's on bottom. Because one of our exceptions is if there's a 0 in the denominator, then we have issues. So I need to solve and figure out when does this whole denominator equal 0. So that's x squared plus 2x minus 3. When does that equal 0? And this is where we really jump into algebra. I mean, this is college algebra, and we have to remember back and how do we solve these quadratic formulas when we have an x squared like this set equal to 0. And we learned a lot of different ways to do that. But one of the ways is with factoring. And so it's like the reverse of foiling, where we have a binomial times a binomial. And we say, okay, this is x squared, so that means I'm going to have an x and an x. And then we have a minus here, which tells me I'm going to have a plus and a minus inside of my binomials. And then here's the nice thing, though, about this example in particular. We need factors of 3. Well, the only factors of 3 are 1 and 3. So I need to put those in place here so that when I subtract them together, I get a positive 2. So I'm going to put 3 here and 1 here. Because now if I FOILed, I would have x squared minus x plus 3x minus 3, which would get me right back up here. Now that I have these 2 binomials written this way, I'd have x plus 3 equals 0, so x equals negative 3, and I have x minus 1 equals 0, so x equals 1. So in our first example, our only trouble spot was when x equals 7. But in this new example, if x is -3 or if x is +1, then we're going to have troubles. So our domain is going to be a little bit more complicated because now I have to eliminate out both of those points. So I have the domain is, again, you start from -infinity and you go all the way up until you hit one of your trouble points. So whichever one is the smallest trouble spot, you're going to hit first. That's -3. You're going to union that and you're going to go from -3, and then instead of going all the way to infinity, we're going to just go until our second trouble point. And you would do this as many times as you needed to eliminate out all of your trouble spots. So this one only has 2 trouble spots that we're trying to get rid of. 1 to +infinity. So we had 2 trouble spots, so we have 2 unions. In the first one, we had 1 trouble spot, so we have 1 union. I think you kind of get the picture. If we had 3 trouble spots, we'd have 3 unions, and so on and so forth. So this time we had to get rid of both of those spots, though, because both of those would give us 0 in the denominator, which would cause problems for our function, because we cannot have 0 in the denominator. All right, let's look at h. h of x equals x to the third. Sorry, my last box kind of hit that. X to the third plus the absolute value of x. Now here's the question. Do I have a denominator that x is in the bottom of? Like a fraction where x is in the denominator? No. Do I have x underneath an even-rooted radical? No. So I don't have either of those 2 cases. So that means my domain is just simply -infinity to +infinity. There are no trouble spots for this function, so I don't have to eliminate anything. So the domain is -infinity to +infinity. Okay. Last example here, we have j of x equals the 4th root of x minus 1. Now this was the other situation that was listed as like an issue or something that would cause an issue with your domain. It was an even-rooted radical with an x underneath. Now, the problem here is not that we can't take the 4th root of 0, because here we were trying to figure out where the denominator equals 0 and eliminate those points. That's not the problem here. We can't take an even root of a negative value. So we need this x minus 1 to be greater than or equal to 0. It can equal 0, that's totally fine. But if this value underneath your radical goes negative, we don't do that right now because that would give us an imaginary or complex number, and we don't play around with those right now. So I need the x minus 1 to be greater than or equal to 0. Well, the nice thing is that even though this is an inequality, I solve it pretty much the same way as an equation. I'm going to add the 1 over to the other side, so x has to be greater than or equal to 1. Now this time, what I found is not that like there was just one trouble spot. There's a lot of trouble spots because I need x to be greater than or equal to positive 1. If x is less than positive 1, like let's say x is 0. If x is 0, then I have the 4th root of negative 1, and that's the issue. That's where I get the problems. So I have a whole range of values for x that I can't include now in my domain. Because if x is less than positive 1, then I have issues. So my domain then, in this case, has to be such that, my notes are wrong. My domain has to be x is greater than or equal to positive 1. So if x is greater than or equal to positive 1, then that means that positive 1 is actually my lower limit. And I do include it with the squared off bracket because if I put a 1 in here, then I'm taking the 4th root of 0, which is totally fine. because I can take a square root of 0 or a fourth root of 0 or whatever, and it's not going to change anything. And then I'm going to go all the way up to infinity. This is my domain. Let me just go ahead and show you, though, for a second. My notes are wrong. I'll have to go change that. I did the opposite, so don't look at that. This is the correct answer. So when you're doing the radical one, like where there's an exemption for the radical, what you're finding is that there's a whole range of answers that you cannot include in your domain. When you have x in the denominator of your function, there's going to be one value or two values or three values. There's going to be a couple of values that you have to get out of your domain. When you're dealing with the radical, there's going to be a whole bunch of values that you're eliminating from your domain. So you do have to be careful on that. I did put a little star note in your notes, if you're looking at it, that if this had been, I'm going to put j star of x, and it was the third root of x minus 1, then the domain would be negative infinity to positive infinity, because the only issue arises if we are taking the even root of this value. If it's an odd root, like a third root or a fifth root, then that's not going to have any play on our domain at all. So it's only if this value out here is even. So you do want to be careful about that.
Hey, so the last examples that I wanted to work with you that are worked in the notes are actually this example number 10, which is from your textbook. This can be found on page 24 and then continuing on into page 25 of your textbook, which you can access via the Pearson My Math Lab site. And so with example number 10, it says, using the graph of the function, find the domain and the range of each of the following functions. So this time you have to give both the domain and the range. And because this is an example that is worked out like in your textbook, it actually gives you the examples. So I'm just going to kind of talk through it and show you how this kind of works. So for A, we have f of x equals 1/2 x plus 1. So we have this line. They graph the line for you. So the question then becomes, does it pass the vertical line test? And it does, because it says this is our function. And we're going to use the domain then and the range. So if I look at this equation, I don't have x in the denominator of a fraction. I do have a fraction, but x is not in the denominator. So I don't have any trouble spots from that. And I don't have any radicals. And so when that's the case, then the domain is going to be the negative infinity to positive infinity always. And then if I look at the graph, because it is a linear line, every y is also going to be hit. So the range then is going to be negative infinity to positive infinity for A as well. B, though, as you can see, it does have the x under the radical. So this is one of those times when we're going to have some trouble spots. And that's when we want the x plus 4 to be greater than 0, greater than or equal to 0. It can equal 0. That's totally fine. So if we are working that out, let me open up something real quick. So it's not going to open it up. If we are working that out, though, which you could open up my notes. Let me show you my lecture notes. Oh, handouts. Excuse me. Chapter 1, section 2. Open up my lecture notes. So I don't need it to work. I just need my notes. Thank you. So if you look, I guess I only gave you the answers because I kind of thought we would work through these together. But we have x plus 4 would have to be greater than or equal to 0. So we would we'd solve that and it'd be x is greater than or equal to -4. So when x is equal to -4, we would have 0 under there, which is totally fine. So we can include the -4 and then we go up until positive infinity. Now this does affect our range though, and you can see that even in the picture. Look at our range, look at the y values that we get. We can never get these negative y values, and so we can't include those in our range. And so our range then is only going to go from 0 up to positive infinity. We aren't going to have any negative values because you can't take the square root of an even square, like an even root, and get a negative value out. And so our domain then goes from -4 to infinity and from 0 to positive infinity. So sometimes your range will be affected as well, depending on what happens with your domain. If we look back at C is drawn here on the right, but C is x to the third minus x. So is there an x in a denominator? No. Is there an x under an even root? No. So then your domain is negative infinity to positive infinity, and your range is negative infinity to positive infinity. So that doesn't change anything on that one. The same thing is true. We can kind of skip ahead. Look at E. E is right below C right here on this page. So f of x equals x to the fourth minus 2x squared minus 3. Again, there's no fraction where x is in the denominator, and there's no even root. So once again, your domain would be negative infinity to positive infinity, and your range would be negative infinity to positive infinity. So that's kind of nice. Is that correct? No, our range would be different. So our range would be affected here because if we put in, like if we look at the picture, which I can't show you, excuse me, oh, it's right there. Page buttons on the bottom. If we graph it, then look what happens. We have this weird W graph. So while our domain does include all the real numbers, or negative infinity to positive infinity, our graph actually doesn't. Even though we do include all the x's, because of the shape of our fourth degree function, which we're going to learn a lot more about as we progress through the semester, we're going to see that our y value only goes so low as -4. It never goes to -5 or -6 or -10. So our range is actually limited. We only go from -4 all the way up to positive infinity. So we do have to be slightly careful about that and actually putting our graph in there. I believe all of your homework problems, they give you the graph and they ask you the domain and range straight from the graph. So you're not in charge of graphing some of these. Now some are. We did do that problem earlier where we did the point plotting system and we did graph an equation. And then from that, they could ask you further questions where they could ask you what is the domain of that graph and what is the range. And that's where one of these situations could come in. So just because the domain is negative infinity to positive infinity doesn't guarantee that that's what the range is as well. It all depends on what the equation is that we are playing around with at that point. Okay, let's go back so we can see what D is. D, we have f of x equals 1 over x minus 2. So this is exactly like the one we just did earlier in the notes, where we can't have 0 in the denominator. So we have to set that x minus 2 equal to 0 and solve. We do that and then we find that x equals 2. So we need to eliminate out that 2 from our domain. And when we eliminate out that 2 from our domain, or it's right here, we have negative infinity to 2 union to positive infinity. Now, here's what you need to think about though, is in this equation, if I put 2 in there, what value do I get out? Well, I would never get, I don't get anything because I get 1 over 0, which is not allowed. So this is where the graph comes into play, because right here is the graph of D. So look what happens. We get really close to that x-axis, and then we shoot off, and then we come back down and we shoot off. But we never actually touch this x-axis, do we? We get really close, but we never touch. And it's that not touching aspect that affects our y, because right here on our x-axis is y equals 0. So we can't ever equal 0. And so our range then will go from negative infinity to 0 union 0 to positive infinity, because based on this graph, we never touch that y value of 0. And so we have to eliminate that from our range. Okay. Oh, sorry. I need to go back a page. The last one is f. F, we have f of x equals the square root of 4 minus parenthesis x minus 3 quantity squared. So there's a lot of stuff going on in here. But the big thing, the most important thing, is the fact that we do have an x underneath the radical, and the radical is an even root. It's a square root. So we'd need to take 4 minus parenthesis x minus 3 quantity squared, and we need it to be greater than or equal to 0. Now you could do the algebra for that, but I'm going to pretend like they gave us the graph straight out of the gate. And this is the graph. And if they give you this graph, then you look at it and you say, okay, well, what x values are at play here? Which ones give us part of the graph? And if you look at the graph, it's just this half circle. And this half circle goes from 1 to 5. So that is your domain. Your domain goes from 1 to 5. And notice that there's filled in circles at the endpoints. That means we do include the endpoints. So we're going to have those squared off brackets for our endpoints. So that's our domain. Now the range is your y value. So you need to look at how high up or how far down it goes, and that will tell you your range. So if we look at this half circle, the smallest y value is going to be right there on the x-axis. That's 0. And because it is a filled in circle, we do include that in our range. So we're going to use a squared off bracket 0. And then if you look at the graph, it goes all the way up until y equals 2. So that y equals 2 bit is right there. And so we also include that because it's a filled in graph. And so sometimes when you're doing these problems as you progress through, just looking at the graph, you're going to ask, okay, what is the highest value for x and what is the lowest value for x, or what is the highest value for y and what is the lowest value for y? And that's what's going to really be beneficial as you are trying to identify the domain, which is your x values, and your range, which is your y values. And then also remembering, though, there's only those two specific cases that really requires us to remove points from our domain. And that's when x is in the denominator of a fraction, or when x is underneath an even rooted radical.